Let us begin the second session of this morning. And before we begin the session, I'd like to make an announcement that tomorrow in the coffee break, there will be a conference photograph actually just down below over here in this building. So try to be there. Sorry? In the coffee break, in the morning, sorry. Okay, there's a degeneracy. Thanks. All right, so the first speaker is Shiraz Minwalla, Nonlinear Fluid Dynamics from Gravity.
Okay. Okay, so my talk today is titled Nonlinear. Okay, so my talk today is titled Nonlinear Fluid Dynamics from Gravity, and this is an outline of my talk. The outline will follow us through the talk, so I won't read out all the elements in the outline. My talk today is based on 3 papers that I've written with various collaborators and 2 projects in progress with several other collaborators soon to appear. I wanted, especially in this list of collaborators, to perhaps inappropriately emphasize the role of my 2 exceptionally good PhD students, Shayantani Bhattacharya and R. Lognayagam, whose role in all these projects has been absolutely crucial, and they're fantastic. Okay. This work, of course, builds on work by many other people. The immediate precursors to this work was very important work by Sohn, Starinets, Kovtun, Policastro, Yannick, and collaborators, many other people. And since our work has been followed up in many important papers, and this is only a partial list of references. Okay, so let's start. So, the introduction. Consider any large N gauge theory, and let rho m of x denote the set of single trace gauge invariant operators of the theory. According to general lore on the behavior of large N gauge theories, it should be possible to rewrite the path integral of this theory in terms of these trace variables in the following form. A path integral over the trace variables is function of x times exponential of minus n squared times some function of these trace variables. These trace guys appropriately normalized. That should have had a 1 over n there. Okay. It follows immediately from this equation that the large N gauge theories are effectively classical when rewritten in terms of gauge invariant variables. That follows because n squared becomes very large and you can do a saddle point approximation of the path integral. Now, in 1997, Maldacena understood what the effective classical system for large N equals 4 Yang-Mills theory was. He explained that the effective classical system of classical dynamical system for this theory, large N classical system, was 2B supergravity and ADS 5 cross S5. The values of various trace operators could be given a solution of gravity on ADS 5 cross S5. The values of various trace operators could be read off from the fall-offs of the various gravitational fields as you approach the boundary of ADS. So this was very beautiful. However, there's a slightly uncomfortable feature of it. And that feature is that the the bulk evolution equations of 10D supergravity, which are elegant and local in the bulk, map to unfamiliar, non-local, and complicated-looking evolution equations when translated directly in terms of the expectation values of trace operators. Okay? And so it would be nice to better understand what 2B supergravity directly implies for the dynamics of these rho n's. Of course, there's a prescription in principle, but it would be nice to flesh that out in some detail. Okay, so in this talk, what we're going to do is some of that. We're going to study rho n dynamics, the dynamics of these trace operators, in a universal sector, I'll explain this in a moment, and in a long distance limit, I'll explain that in a moment as well. And we'll show that in this particular sector and in this particular limit, the dynamics implied by the gravity equations for these trace operators become local and familiar boundary dynamics in a sort of very nice way. And this may help us, this may be the first step in understanding more such the boundary equations better. Okay, so I should immediately explain what I mean by this universal sector. So far I've been talking about n equals 4 Yang-Mills theory, but let me broaden my canvas a little bit. Let me look at any field theory that has a dual description in terms of a two-derivative theory of gravity interacting with other fields on an ADS space. Okay? So the bulk equations of motion we're considering are two-derivative gravity interacting with other fields, and the only property of these equations that I'll require is that these equations admit ADS d plus 1 as a solution. Okay, now it's a simple fact to verify that every such theory admits a consistent truncation to Einstein gravity with a negative cosmological constant. In this truncation, all fields other than the Einstein frame metric are simply set to their ADS d plus 1 background values, and the Einstein frame metric fluctuates. The equations of motion, this is a consistent truncation, the equations of motion for these metric fluctuations are simply the Einstein equations with a negative cosmological constant. Now this observation has an interesting dual implication. You see, usually the dynamics of all these trace operators is complicated and all traces couple with each other. However, in this universal sector, okay, we've got decoupled dynamics of the stress tensor, and it's universal because it doesn't care about the details of the equations in the bulk. As long as the bulk equations were two-derivative theory of gravity interacting with other fields, you get the same dynamics for the stress tensor. So you've got a simple subsector which is universal in all such theories. Okay, that sounds interesting and sounds like a place to look at. Okay, so in this talk we're going to look at this universal subsector and look at a particular limit of this subsector, sort of long wavelength limit. And we will conjecture and largely demonstrate that the set of all regular long wavelength solutions to Einstein's equations with a negative cosmological constant in d plus 1 dimensions is identical to the set of solutions of the boundary Navier-Stokes equations with holographically determined values of transport coefficients in d dimensions. Okay? So, in this talk and building on other people's work, we'll display an equivalence between the Einstein equations written down long ago with the Navier-Stokes equations written down even longer ago. Okay? So this will be another one of these examples of connections between classic equations of physics that uncovered by string theory. We've seen many such examples. Okay, so let's start. Okay, so this universal sector that I told you about had Einstein's equations with a negative cosmological constant. Those are those equations there. Chosen the value of the cosmological constant so that there's a solution to these equations with ADS d plus 1 space with unit radius. Okay, so that's one solution to these equations, but of course there are several other solutions to the equations, and I'm going to write down another exact class of solutions. The class of solutions I've written down here is the solutions corresponding to the familiar black brane solutions that Steve Gubser wrote down or alluded to in his talk in sort of Graham-Pfefferman type or Schwarzschild type coordinates. And I've made a slight generalization here from the metric that you often see by allowing for taking the usual solution, which is the black brane at rest, and boosting it. This is a large coordinate transformation, so in some sense it's the same solution. It's an exact solution to Einstein's equations. It represents a black brane at temperature T and velocity u mu, where u mu is some d plus 1 velocity on the boundary. Okay? Good. So those are some exact solutions, a small number of exact solutions to these equations. Now, if you look at the black brane solution, it's easy to use the usual rules of ADS CFT to compute the dual boundary stress tensor. And you find the following formula. The stress tensor up to a constant is T to the D times this this linear combination of the metric and the velocities. Okay. Now, there's a sort of, given the stress tensor, there's a sort of invariant way of reading off the velocity and the temperature that corresponds to the stress tensor. And that way can be thought of as thus. If you take this formula and contract it with the velocity, you find that what you get is something proportional. You get the answer is proportional to the velocity times a constant times t to the power d. So the velocity vector is an eigenvector of the stress tensor, and t to the power d is its eigenvalue. In fact, it's the unique time-like eigenvector of the stress tensor. Okay? Now, we've worked all this out for a very simple solution of Einstein's equations, but I'm going to generalize the idea. So given any solution of Einstein's equations, there's some dual stress tensor. The stress tensor varies as a function of where you are. And I'm going to use an equation like this, now made local, to define what I mean by the velocity of that solution and the temperature of that solution. Okay, the velocity is the unique time-like eigenvector, and the temperature, t to the power d, is the eigenvalue. Okay, we'll need these definitions as we go along later. But now let me tell you exactly what problem I want to address. Okay, consider an arbitrary evolution of the stress tensor on the boundary. And though I won't stress it in this talk, everything that I'm doing has enough freedom to allow for an arbitrary metric on the boundary. So our space is not constrained to be ADS as we go to the boundary, it's only locally ADS. Okay? Now, let delta x denote the minimum length scale in the variation of the stress tensor and the metric on the boundary. You know, we should specify this in more detail, but I won't have the time to do that in this talk. And let epsilon of x denote 1 over t of x times delta of x. So epsilon of x is a measure of how fast things are varying on the length scale set by the equilibration length scale, namely 1 over the temperature of the theory. Okay, when epsilon is small, everything is varying on distances large compared to this equilibration length scale. Okay, now this is the question we're going to address in this talk. Given an arbitrarily slowly varying boundary stress tensor t mu of x, what are its boundary equations of motion? That is, under what conditions can this function t mu of x be obtained from a regular solution to Einstein's equations? Okay? When these conditions are satisfied, what is the bulk dual space-time corresponding to this t mu of x? So this is a question we're going to largely address in this talk. Okay? And we're going to address this question only in the limit of very small epsilon of x, and we're going to address it in perturbation theory in epsilon of x. And the way we're going to address it is by constructing a large class of solutions that have this property, that they're slowly varying, and then we will conjecture, and there's some evidence for this conjecture, that these are all the solutions that have this property. Okay, so that's the question we plan to address in this talk. Now, fine. So how do we do this construction? See, what we want to do is construct some solutions which have this slowly varying stress tensor. Now we use intuition from the boundary theory. If in the boundary, if you've got some configuration which is varying slowly on the length scale set by equilibration, you expect this configuration to be locally thermalized. The dual statement to that in the bulk presumably is that the solution can be foliated into tubes, each tube of which is locally the solution, or near a solution, locally approximately a solution that corresponds to a tube inside a uniform black braid, some temperature and some velocity. The important question here is, how do these tubes move into the bulk? They hit the boundary somewhere, but what's their shape as they move into the bulk? Okay, there's a naive guess for this, for the answer to this question. And the naive guess is, well, suppose these tubes just run along constant x mu in Schwarzschild coordinates. That is, suppose that we'll construct metrics that look approximately like the black-brain metrics that we wrote down before, except that the velocities and temperatures are allowed to vary in space. Okay, this is a naive guess. Unfortunately, I think it's wrong. This metric is not regular for an arbitrary choice of t of x and u mu of x. And also this metric has an intuitive problem with causality that I'll now explain. The problem is this. You see, we're keeping track of allowing variations of the boundary metric. The boundary metric is in our hands. So suppose we got some flow of gravity going on, and then we decide to change the boundary metric a little bit. Okay, that should affect the bulk only in the future light cone of that boundary metric, if we're dealing with a sort of causal problem. The tubes that I drew for you, along which the solution should approximate black brains in Schwarzschild coordinates, are these red tubes that extend from the boundary to, well, morally speaking, the bifurcation point, and they don't have this causal property. Okay, but that suggests what the right answer is. Let's try to look for tubes that go along light rays. So let's try to make a guess that the solution that we'll be looking for is approximately a black brane solution, but written in Eddington-Finkelstein ingoing coordinates. And then we allow velocities and temperatures to be functions of x mu. Okay? So that's the same idea as foliating the space-time into tubes in which the solution is approximately black brane, right? But these tubes then go along ingoing null geodesics. Okay, so that sounds like a better thing to do. And technically it's a better thing to do because when you write down this space-time, as I'll show you in more detail later, this space-time is of course not in general a solution to Einstein's equations, but it has a good property. It's everywhere regular. Okay, it has a regular event horizon. Okay, the other good property that the space-time has is that when temperatures and velocities are constant, it solves Einstein's equations. So you might think, well, these are two good things, so maybe this is an appropriate starting point for perturbation theory, to build up solutions in a perturbation series in epsilon of x, okay, where this is the zeroth order term in perturbation theory. So let's try that. So let's set the metric of our space-time to be gmn0, which is the metric we had on the previous transparency, plus unknown corrections, parameterized by this epsilon of x, and attempt to solve for this gmn of x order by order in epsilon. It turns out that this perturbation expansion is surprisingly simple to implement. The nonlinear partial differential equations for Einstein equations in this perturbative scheme, order by order, reduced to 15 ordinary linear differential equations in the variable r. And okay, now there are various technical comments about how you have to go about solving these equations. You set a certain gauge, sort of background field gauge. The gauge depends on what solution you're looking at. That's convenient for the problem. But I won't stress all of that. The important point is that these 15 Einstein equations, turns out one is redundant. It follows from the other 14. So 14 independent equations, which you can split up into 10 dynamical and 4 constraint equations. I'll quickly explain to you the structure of these equations now. The constraint equations at nth order simply turn out to be the conservation of the energy momentum tensor of the solution built up to n minus 1th order. The important point about this is that the constraint equations at nth order do not involve the fluctuation gn. So they're constraining the solution that you've already computed. Okay? The dynamical equations, on the other hand, constrain gn, the fluctuation at nth order, and they take the form a homogeneous operator acting on gn is equal to source. Okay? Here m is a homogeneous differential operator in R that is the same at every order. Sn is a source function that is independent of gn and is determined by the solution up to n minus 1th order. Okay, now it turns out to be possible to exactly solve the equation mgn is equal to Sn for an arbitrary source function. Of course, for any given source function, there's a family of solutions to the equations, which differ by solutions to the homogeneous equation, mg is equal to 0. However, provided that the source function Sn is regular at the horizon and dies off sufficiently fast at infinity, conditions which I'm not sure have been proved, but at least appear to be satisfied in perturbation theory, the solution to this equation is unique, subject to the following requirements. The first requirement is sort of the trivial one. It's the one at infinity. We want the solution that we construct to correspond to the boundary metric g mu nu of x. Okay, so that sets the condition on the non-normalizable part of the solution. And we also want it to correspond to the velocity u of x and t of x in the sense that I defined these velocities and temperatures in the early part of my talk. Okay, so that we know what solution we're talking about. The second condition is at the heart of the physics of the problem. It's a condition at the event horizon, or the event horizon of the unperturbed solution. R is equal to 4 pi t by d. And we require that our perturbations don't spoil this nice property of our initial ansatz, namely the regularity of the future horizon. And what's really nice is that these two conditions are enough to uniquely determine the solution. Okay? Now this is very important because naively, from Graham-Pfefferman type intuition, you would have expected an arbitrary conserved boundary stress tensor to determine a bulk metric. So you would have expected, say, in 4 dimensions, there to be a 9-parameter set of solutions parametrized by boundary stress tensors, okay, subject to conservation for all the solutions. However, the fact that these solutions are unique tells you there's actually a 4-parameter set of solutions, parametrized by velocity and a temperature. So somehow we've traded the variables of gravity, namely a metric, for the variables of fluid dynamics, namely velocity and a temperature. Any deviation away from this distinguished set of solutions is singular. Okay, so now once we've solved these dynamical equations at nth order, we can construct the stress tensor dual to a perturbative solution. The stress tensor is uniquely determined as a function of, since the whole process was unique, everything is determined once you've given u mu of x and t of x. So the stress tensor is uniquely determined as a function of u mu of x and t of x of nth order and derivatives. Now recall that the constraint equations are the divergence of the stress tensor is equal to 0, but this equation, the conservation of the stress tensor, together with the specification of what the stress tensor is in a derivative expansion of velocities and temperatures, has a name. It's simply the generalized Navier-Stokes equations. Generalized because Navier-Stokes worked it out first order in the derivative expansion, but you can keep going. Okay? So summary. We found an explicit map from the space of solutions of the generalized Navier-Stokes equations in d dimensions to long wavelength solutions of Einstein's equations with a negative cosmological constant. It's key that the requirement of regularity of the horizons ensured that this map was locally one-to-one in solution space. We have not shown that this map is globally one-to-one. That is, there could be other solutions far away from the class that we've looked at of Einstein's equations that are not fluid dynamics, but for various reasons that I won't go into, we doubt that. So our conjecture is that this is all the slowly varying solutions of Einstein's equations, the negative cosmological constant. Okay, and I've already described this Graham-Pfefferman counting for you. The key point was that of all the possible variations you could perform by varying the boundary stress tensor, only d of these variations are regular at the horizon. The rest are singular. So we trade a metric for a velocity and a temperature. Okay, now we've explicitly implemented our perturbation theory to second order, and this is the metric. I'm showing you these complicated formulae just to show that they exist. Okay, and the dual stress tensor to the solutions given by other set of complicated formulae. Let me quickly tell you a little bit about the answer. Looking at the dual stress tensor. The stress tensor starts off its life in this form, no derivatives on the velocities and temperatures, then picks up a term with one derivative on velocity and temperature, then has terms with two derivatives of velocities and temperature. Velocities, right. The coefficient here is a thermodynamic parameter that Steve Gubser talked about in the morning. The coefficient here is related to the viscosity, and our calculations are consistent with this by now classic result of the viscosity by entropy density equals 1 by 4 pi. The coefficients here are unfamiliar and new. They're second order corrections to fluid dynamics, and it turns out that you can parameterize these coefficients as a linear combination of 5 independent conformal terms from general symmetry principles. We get values for these 5 coefficients. Okay, perhaps the only qualitative thing that I would like to say is that the values of these coefficients disagree with a formalism for second order, higher order fluid dynamics that had been proposed by Israel and Stewart, and that's widely used, for instance, in simulations of Rick. I said Rick just for one. He wanted me to say Rick sometime in my talk. Okay. Okay, so recall that, the one thing I want to stress here is that recall that our results are universal. Okay, they apply to any theory, two-derivative theory of gravity, that has ADSD plus 1 as a solution. So this is an infinite number of theories. This universality, remember the two-derivative theories work only when the field theories are very strongly coupled. So suggests a certain, at least some universality of strongly coupled field theories. So I take this to say that this should yield the correct order of magnitude estimate of transport coefficients for any strongly coupled CFT. It's probably the best estimate you have if you know nothing else about the CFT. Okay, the last thing I wanted to say about our results, but I'm skipping it because of time, is that our results are consistent with wild covariance. You know, there's this lovely fact about ADS-CFT that you take the same bulk solution and you slice the boundary in different ways, and you get different boundary solutions that are related by conformal transformations. So that puts a constraint on the possible solutions of fluid dynamics in our theory, and in a way that I will not describe to you, our solutions meet this consistency test. Okay, great. More about regularity. You see, our solutions are singular at r equals 0. The singularity was like the singularity and originated from the singularity of the black brains that were the starting point of our construction. But we don't worry about the singularity of the black brain because it's shielded by a regular event horizon, regular future event horizon. So it's an important question to ask, are our solutions also shielded by regular future event horizons? The answer to this question, under certain assumptions, is yes. And more interestingly, not only can you argue that these event horizons exist, you can also construct these event horizons, these manifolds, perturbatively in epsilon. This is quite non-trivial. It's generally hard for a solution of general relativity to construct these event horizons. The perturbation theory in epsilon that makes life easy. In order to really understand these event horizons, you have to know something about the long-time behavior of these solutions. A sufficient, though far from necessary, condition is to assume that at long times they go over to uniform brains. This is not a very restrictive assumption if you think about it. You would expect that to be true of any solution of fluid dynamics, which is a finite fluctuation around finite energy fluctuation about uniform fluids, but I won't dwell on that. Okay. So now, given that you know something about the long-time behavior of the solutions, the event horizon of the dual bulk geometry is a unique null manifold that reduces to the event horizon of the black brain that you know is the correct event horizon at large times. So this sets up a well-defined mathematical problem that you can try to solve. You can find the null manifold that meets some future conditions. And it turns out to be really easy to solve these conditions in the derivative expansion, and you get this answer. Again, some complicated looking formulas. The important thing to note is that at leading order, RH is 1 over the local temperature, okay? And then is corrected in a derivative expansion of velocities. So the position of the event horizon at x mu depends locally on the temperature and velocities at x mu. That's quite incredible. You know, in this situation, the event horizon is not this non-local beast that we've all learned to fear. Okay, so now we can put our control over the event horizon to practical use. I don't have the time to spell out the details of all of this, but basically, see, we know the event horizon, so we can define an area form on the event horizon. Now, it's a sort of classical theorem of general relativity that this area increases locally. Okay? We can take the mathematical statement of this classic result of general relativity and somehow pull it back to the boundary and use that to construct an entropy current on the boundary, an entropy current which is locally positive divergence. Okay? So this entropy current is a sort of local H function of our fluid dynamics. You know, it's something that locally, it tells you that there's a quantity that locally always increases. Establishes the local irreversibility of these flows. Okay, there's lots more to say about it, but, well, perhaps the most important thing to say about it is that this is the formula for it, but let's move on. Okay, fine. Now, all our general constructions, it's possible to test our general constructions against an exact class of solutions of general relativity. Okay, the solutions in question are stationary rotating black holes in global ADS. These solutions are labeled by their mass plus integral value of d by 2 commuting angular momentum. They're simple solutions and they've been known for a long time. Okay, so now there's a limit, namely when these black holes become very large, their temperature becomes very large, when these solutions meet the criteria for being described well by fluid dynamics. So we can check whether our constructions actually works out with these solutions. So the first thing we did was to take these solutions, work out the temperature and velocity that corresponds to these solutions using our general prescription, and then take the solutions and rewrite them in our gauge in terms of this velocity and temperature, or just the velocity actually. And it turns out that these complicated looking solutions look very simple when rewritten in this gauge and in these variables. Okay, so this is an exact result for the metric of these black holes. Then you can take this exact result and study it. So there's three things I wanted to say about it. Firstly, the perturbative, the stress tensor dual to these black holes is exactly reproduced by the stress tensor, our fluid dynamics stress tensor up to second order. The second thing, the full metric of the black hole when it's not rotating, the Schwarzschild metric, is also exactly reproduced by the second order fluid dynamical results. The last thing to say is that in the general case, the full metric is not exactly reproduced. Its expansion up to second order is reproduced by our results, but there are higher order corrections. So that's sort of interesting because you can study these corrections, check check the radius of convergence of the fluid dynamical expansion for these solutions. It's finite, it's 1 over T. It all works very nicely, but I don't have the time to describe it in more detail. Okay, quickly. So, forcing and charges, 2 generalizations of all of this. Okay, see, so far we've been talking about these nice universal equations. Okay, now you can try to solve bulk equations that have more fields than the Einstein gravity. Okay, the price you pay for that is that now your equations are no longer as universal as the ones we studied. So that's not so nice. The gain you get is you get more solutions and more interesting dynamical behavior. Okay, so you can take it or leave it, but anyway, this is what we did. So the additional fields that you can add are of 2 sorts. The first kind is a bulk gauge field that corresponds under the ADS-CFT dictionary to a boundary conserved charge. The second kind is a field that doesn't correspond to a boundary conserved charge. Everything else. Okay? And these 2 kinds of additions are qualitatively different. We've worked out one example of each. Okay. They're qualitatively different because when you add gauge fields, you enlarge the set of fluid dynamical variables to include charge densities apart from temperatures and velocities. Okay. On the other hand, if you add the other kinds of fields, you don't enlarge the variables of fluid dynamics, you just change the equations for fluid dynamics. These equations get forced. So let's see. So the example of the second kind of field not corresponding to conserved charge is the dilaton. In 4 dimensions, we worked out the same story with the Einstein dilaton system, and we found once again the correspondence between regular long wavelength solutions to the Einstein dilaton equations and the Navier-Stokes equations that are forced by a forcing term that depends on the dilaton. We know this to more precision that I've written down here, but okay. There's some interesting solutions you can write down, but forget that. The second kind of generalization is to include gauge fields. So once again here, this is not universal, we have to look at a particular system. So we looked at 2B supergravity on ADS 5 cross S5. We looked at the sector with only diagonal combinations of SO6 gauge fields, which admits a truncation to the U1 Einstein-Maxwell system with a gauge term. Once again, we can set up the perturbation theory, and the end result is a reduction to the charge Navier-Stokes equations, conservation of the stress tensor, conservation of the current, with holographically determined expressions for charge, current, and stress tensor and a series of derivative expansions. Okay, you can check, we've only worked out this construction first order so far, but we're in the process of doing it to second order, and you can check our first order result against charged rotating black holes. It all matches perfectly, and the contribution of the Chern-Simons term is important to resolving a puzzle that we had a year ago when doing this comparison and not getting it to work, but I don't have the time to describe that to you. Okay, there's also an interesting story when you add charge with the extremal limit. This is a question of whether the extremal limit commutes with the description in terms of fluid dynamics. And there's an interesting story there that we haven't quite cleared up, but okay. Fine, so I'm at the end of my talk, and I'll end with some ruminations. Okay, firstly, that's the trivial stuff. And the results that we've worked out almost certainly admit various generalizations. You can generalize to non-conformal backgrounds, like D-branes in other dimensions. You can generalize to confining gauge theories. You should find interesting new configurations like fluids with a boundary, like these plasma balls that have been discussed before, and so on. This is almost certain to work out, but maybe technically tough to do. Okay, but the more interesting questions are, what can you do with all of this? You found this nice equivalence between 2 classic equations of physics, about both of which lots is known. Okay, this should be good for something. Okay. So, what could it be good for? I'm not sure, but perhaps, it's true that you can, well, it seems to be true that you can set up situations in gravity that are dual to turbulent fluid flows. For instance, if you take the dual to some fluid that's rotating very fast on the sphere, okay, you can easily set it up so that all our approximations are obeyed and it has high Reynolds number. Okay. So this should tell you something. Perhaps gravity can be used to tell you something about gravity, of a fluid dynamics. Okay, we can discuss deep issues like we started with Einstein's equations at the time reversal invariance, that was broken. Because we required regularity of the future, not the past horizon. What does that translate to in field theory? Cosmic censorship, the conjecture that singularities don't form in the process of thermalization, the process of black hole formation, seems to be related to a conjecture that correlation functions in the process of thermalization are regular in field theory. Yeah. Why are solutions to this effective action S of m with energies of order n squared, why are they thermal? The solutions at order energies of order 1 are not thermal, they represent states. Increase the energy, they become thermal. Why is that? And most sort of importantly and perhaps deeply, all of this, Einstein's equations are the boundary Navier-Stokes equations. Now the boundary Navier-Stokes equations come from looking at collective motion of gluons and atoms and so on. I mean, they're not the fundamental description of the theory. There's an effective thermodynamical description of the theory. So at least there's a regime in which Einstein's equations appear to be an effective thermodynamical description. So Einstein's equations, space-time possibly, some effective thermodynamical description. Is that correct? Can you make it precise? Is this the same thing that Jacobson has been saying? And so on. Okay, I hope that we will soon be able to get a concrete hold in one or more of these important sounding questions. Thank you. Sorry for the overrun.
Yes.
So, in the gravity side, you have the condition that the class of solution you're considering is wavelength in the appropriate sense.
Yes.
And in Navier-Stokes side, are there any conditions? Because one of the interesting questions about Navier-Stokes equation is that when its solution develops singularity.
Right. Right. So, the nature of the fluid dynamical equations is a derivative expansion. So the equations of fluid dynamics also accurately approximate microscopic physics only in the long wavelength limit. So the gravity solutions, the solutions we found for the long wavelength limit, they map to solutions of fluid dynamics when and only when fluid dynamics is an accurate representation of boundary dynamics. Now, you could have solutions.
Can you sharpen that condition?
No, very easily. You see, yeah, it would be easier with the black. Yeah. Okay. You see, what the fluid dynamical expansion is an expansion of the stress tensor in a power series in derivatives. So derivatives, for instance, of the velocity. But dimensionally, each time you have a derivative, you need to have a length scale. In this conformal theory, the only length scale you could have is 1 over temperature. There could be a function of the coupling, but in gravity the function of the coupling is order 1. Okay? So the derivative expansion here is an expansion in derivatives divided by temperature. Now if these derivatives if things start varying on order of the temperature, all orders in this expansion are equally important. So to work with the equations truncated to first and second orders is simple. Yeah?
Thank you.
Yes.
First order derivative expansion is not without also.
Yeah.
You have to go to second order. You know what happens to third order?
Well, you see, first order hydrodynamics is non-causal, but the non-causality is only applies to those solutions that aren't accurately described by first order fluid dynamics. So this solution is manifestly, the bulk solutions are sort of manifestly causal. But if you truncate to any given order, I think there's a good chance you'll always have a problem with causality, except that these problems will be in a regime that you shouldn't work with, given that you've truncated to that order. So I haven't studied this question in detail, but yeah, I think it will work as well as it should.
Let me answer that. In going to third order, you would get additional coefficients.
Yes.
Would they be of hydrodynamic origin? Would they be properties of your thermalized system, or would they be artifacts?
No, they would be properties of the system. You see, I should have stressed this, that this expansion can be carried on to every order. This perturbation theory we worked out to second order, but it's well defined and carried out to 27th order. And gravity will uniquely predict all of these coefficients. You see, there will be some coefficients determined by the theory, but uniquely predicted. They're not artifacts. You need each of these coefficients to describe solutions of Einstein's equations. So they're determined by the underlying dynamics of the system. Perhaps I haven't understood your question.
Maybe. Just one last quick question. Yes.
This expansion in epsilon, this parameter,
Yes.
what happens to it? I mean, the physical picture, the physical equivalence.
I think, can you use the mic, please? I'm sure people can't hear. To press some button, or you use this one.
Okay, thank you. This physical picture that you have an equivalence between Einstein equations and fluid dynamics.
Yes.
This epsilon expansion, when epsilon goes to 1,
Yes.
What happens to the picture?
It breaks down very badly. You see, because Einstein's equations are really 5-dimensional. Fluid dynamics equations are 4-dimensional. How do you see that in detail? Let's look at it in the linearized level. So let's look at a uniform black brane and linearize Einstein's equations around it. Okay, so in the linearized level, you find that the regular solutions are given by linear combinations of quasi-normal modes. Now there are 4 distinguished quasi-normal modes that have the property that omega goes to 0 when their wavelength goes to 0. And hydrodynamics is the effective nonlinear theory of these quasi-normal modes. It's like the Goldstone theory of these quasi-normal modes. However, there are many other quasi-normal modes. They start with energies 1 over T. And there's infinitely many of them. Now when epsilon goes to 0, you'll have enough energy in the variations of your hydrodynamic fields to excite these other quasi-normal modes. So the theory will become infinitely non-local, but the better way to think of it will be that non-locality is a result of integrating out other fields of the energy that you should have been keeping. So the better way to think of it is now a theory of an infinite number of fields, not just velocities and temperatures. So the correct description when epsilon goes to of order 1 is to include more degrees of freedom, which is very different from hydrodynamics.
Okay, I think we should thank Shiraz. So the next speaker is Luis Alday, scattering amplitudes via ADS.